So hello, I'm happy to present our work on the Seesaw algorithm. My name is Nicolau Genota, and this is joint work with Antonio Morgado, José Santos, e Vasco Maqui. So first of all, to give a little bit of background, let us look at the well-known minimal hitting set problem, wherein we are given a set of sets, and we're supposed to select elements in order to hit all of them, and the cost of this hit should be minimal. So we should select the minimal number of these elements, or we can also consider minimizing some weighted sum of the elements. So for instance, here we have 3 sets, blue, red, and green, and I can of course hit 3 sets by 3 elements by choosing some random element from each. However, in this case, in this example, this is not the minimal solution because 2 elements are sufficient. There might be more than one solution. So for instance, here I can change the solution to this and it's still fine. Okay, so this is the minimal hitting set problem, which is well known to be NP hard. Now, what is the implicit hitting set problem? Is when we are not given all the sets all at once, but we are getting them one by one. So imagine that we have this blue and a red set, and I see only these two. So, well, I'll just pick an element that's in the intersection, and that covers both of these. However, now someone gives me another one, this green one, and then I have to add one more element to cover that one, to hit all 3. And now another 4th one comes, and then I have to alter my solution to get still the minimal hitting set. Okay, so I'm not solving one minimal hitting set problem, I'm getting sets one by one. However, the goal is to hit all of the sets, including the ones we have seen, including the ones we have not yet seen. Now, the question is, where do these new sets come from? So for this purpose, we have a predicate on the hitting set that tells us whether we already hit all of the sets or not. And then when I say all of the sets, I mean also the ones that we have not yet seen. Okay, so we always assume we hit all the ones that we have seen, but we use this predicate to determine whether we have also hit the ones we have not seen. Now, if we had not hit all the sets, the ones that we had not seen yet, then we get a new one and we repeat the process. If, however, we happen to have hit all of the sets, then we can stop. Okay, so we're using this predicate to generate new sets, and we're asking whether we can stop already, whether we hit all of the sets, including the ones we had not seen yet. And a remark here, the cost of calling this predicate might not necessarily be polynomial. It can also be not in NP. So an example of this problem is maxsat, where the P is in NP, or minimal unsatisfiable set, where it's also in NP, but we can also imagine generalization where this is outside of NP. Okay, so this is the implicit hitting set paradigm. And now how do we generalize this? So we know that predicates can be seen as functions from 0 and 1. So here the goal is to get the value to the predicate to 1, right? So we're continuing with generating new and new sets until we get P being equal to 1. So the question we are asking, can we generalize this approach to arbitrary functions? Okay, so instead of a predicate, which is in fact just a function between 0 and 1, to arbitrary functions. So this is our setup. So we have one function, which is the cost, which is the same one we had before, which may be, for instance, the number of elements. So to give an example, imagine you want to build a portfolio of solvers solving some set of instances, let's say for some competition. And the cost is the size of the portfolio. Okay, and we have one more function, which we call the oracle. So instead of a predicate, we have a function that just returns some value, and that is completely black box. So we don't know anything about it. And it gives us, in the example of a portfolio of solvers, some sort of score. So let's say the average time or the total solving time of the portfolio of solvers. Okay, and the main difference between these two functions is that the cost can be expressed, can be encoded into, let's say, a SAT solver or an ILP solver, whereas the oracle is black box. Okay, so now we have these two functions, but how do we optimize for two functions? This is a well-known problem. It's not as simple as just minimizing one function where it's clear that the objective is to minimize a function. But what about two functions? So this is where the name comes from. So it's the seesaw paradigm, where we imagine that we have a seesaw and the left-hand side determines the value of the cost function and the right-hand side determines the value of the oracle function. And the goal is to minimize both of them, which might not be possible at once. And we start by minimizing the cost. So we bring the left-hand side completely to the ground. So imagine, let's say we have like a child sitting on the left-hand side, and now we place a different child on the right-hand side, and that starts driving the cost of the oracle function down. And let's say the child is eating some cake, so it keeps on driving the value down, and the seesaw is not completely rigid, so it might be that not necessarily the left-hand side moves. And the end, or the very possible end, is that we drive the cost of oracle all the way down. Okay, so the hard part is how to minimize the oracle function, because this is a black box function. Okay, so how do we go about doing this? So remember that in the implicit hitting set paradigm, we're improving the quality of the hitting set by getting more and more sets that we were supposed to hit. And here the idea is the same. We're getting more sets, which we call cores, and we define them as follows. So imagine you already have some value of the black box oracle function, and now a core is such a set kappa that any candidate that improves on this existing value nu must intersect with this core. Okay, so this is a bit of a mouthful, but the intuition here is that if we want to improve the current solution, we must hit this set. Okay, so again, we have some way of coming up with these new sets, new cores that act as some sort of lemmas that tell us how to improve the value of the oracle function. So again, just to give a small example, we're again building a portfolio of solvers for some competition, and the whole set is S, and we pick some subset S primed, which is our candidate for the portfolio, and that has some score V. And now we start growing this subset S primed as long as the score is not improving. Okay, so let's say the total solving time is not improving. We're adding some poor solvers that are not helping, or duplicate solvers, for instance, or and so on. And once we are done extending it, we take the complement of this, right? Meaning that if we were to improve on the value, on the score of S primed, we have to add a solver from this complement. Okay, so this is an example how to obtain a core in this particular scenario. So, okay, so now what's the general form of the Seesaw algorithm? We always maintain some candidate for the solution, the best value of the oracle seen so far. We also maintain all the cores we have seen so far. And then we loop by first finding a hitting set of all the cores we've seen so far, while minimizing the cost. So we should not forget about the cost, which is the function that is white box. We can see what's inside. We can find it by a SAT or an ILP solver. And then we might update the value of the best candidate if we had improved the value of the oracle. And then we calculate a new core based on the current candidate and the current value of the best value of the oracle function. Now we repeat this until some stopping criterion. Now, what do I mean by this? What are the possible stopping criteria? So let us look a little bit at the behavior of this algorithm. So for this purpose, we draw this picture where we have the oracle function on the horizontal axis and the cost function on the vertical axis. And remember, the Seesaw starts by minimizing completely the cost. Okay, so we definitely start with some point that is all the way down. So here we have this H1 point that is all the way down, and we don't know what's the value of the oracle function, but we're adding new cores that keep on driving the value of the oracle function down until we cannot improve it anymore. Now, what do I mean we cannot improve it anymore while maintaining the cost? Okay, so we get a point that is in fact Pareto optimal, meaning that if we were to improve the value of one of the functions, the other has to worsen. Okay, so we are guaranteed to find a Pareto optimal point while having the cost minimal. Okay, after that, we continue, and again, the process guarantees that eventually we get another Pareto optimal point. We don't know when, but we're guaranteed to get it. So we don't know how many iterations it will require, but we are guaranteed by repeating this process to find the whole Pareto front of these two functions, starting with the Pareto optimal point, which has the cost minimal, and we end with the Pareto optimal point, which has minimum oracle value. Okay, so this is the take-home message. The Seesaw algorithm is able to explore the whole Pareto front while not really knowing much about this oracle function, meaning it's a black box function. Now I'm saying not knowing much because there is a bit of a catch to all this, what I've been saying. There are some preconditions that need to be fulfilled for the algorithm to behave as I just had described. So first, the algorithm will behave correctly if the cost function is strictly monotone. So for instance, the cardinality. Okay, so the standard minimal hitting set problem is clearly a strictly monotone function. Another possibility is that the oracle is anti-monotone. So this is maybe a little bit hard to imagine what it means because we are always minimizing the oracle. But imagine that instead of minimizing, we are maximizing it. So this means that then it's monotone instead of anti-monotone. That's our precondition. So again, if we're talking about the score of a solver portfolio, that is clearly a monotone function because adding a solver into the portfolio can only improve our solving time. Okay, so if either of these conditions are satisfied, the algorithm will behave as we had just discussed. Okay, so just to summarize very quickly, we have introduced a new algorithm that generalizes on the implicit hitting set paradigm by using functions instead of a function and a predicate. So now we have two different functions that we're optimizing at the same time. And the first function is we can say it's a white box function because we can encode it into a solver in an ILP, a SAT or MaxSat. And the other one is black box. The oracle function is black box. And we are exploring the whole Pareto frontier of these two functions under certain conditions. What is the purpose and the usefulness of this? So we can encode or we can optimize black box functions. So functions that are impossible to encode or extremely difficult to encode, right? So we, for instance, tried this portfolio construction and encoding it into Groby, and Groby is already just saying that it cannot handle these kind of constraints because there's too many constraints. Now for future work, the question is whether we can extend this to multiple functions, right? So here we have just two functions. Why only two? Maybe we can have multiple. Another interesting question is, when is such decomposition useful, right? So until now, I was saying, well, this is a black box function because it's impossible or maybe hard to encode into a SAT solver. But let's say that sometimes it is possible, but it does not pay off to encode. But sometimes, yes. So this is a kind of a more general question, in which situations it is useful to encode and which not. Okay, so this concludes my talk, and I'm happy to take questions in the real world.